The Standard Model of Particle Physics is a theory concerning the electromagnetic, weak, and strong nuclear interactions, which mediate the dynamics of the known subatomic particles. It was developed throughout the latter half of the 20th century, as a collaborative effort of scientists around the world. The current formulation was finalized in the mid-1970s upon experimental confirmation of the existence of quarks. Since then, discoveries of the top quark, the tau neutrino, and more recently the Higgs boson, have given further credence to the Standard Model. Because of his success in explaining a wide variety of experimental results, the Standard Model is sometimes regarded as a theory of almost everything. The Standard Model falls short of being a complete theory of fundamental interactions. It does not incorporate the full theory of gravitation as described by general relativity, or account for the accelerating expansion of the universe. The model does not contain any viable dark matter particle that possesses all of the required properties deduced from observational cosmology. It also does not incorporate neutrino oscillations. Although the Standard Model is believed to be theoretically self-consistent and has demonstrated huge and continued successes in providing experimental predictions, it does leave some phenomena unexplained. The development of the Standard Model was driven by theoretical and experimental particle physicists alike. For theorists, the Standard Model is a paradigm of a quantum field theory, which exhibits a wide range of physics including spontaneous symmetry breaking, anomalies, non-perturbative behavior, etc. It is used as a basis for building more exotic models that incorporate hypothetical particles, extra dimensions, and elaborate symmetries in an attempt to explain experimental results at variance with the Standard Model, such as the existence of dark matter and neutrino oscillations. Historical background: the first step towards the Standard Model was Sheldon Glasgow's discovery in 1961 of a way to combine the electromagnetic and weak interactions. In 1967 Steven Weinberg and Abdus Salam incorporated the Higgs mechanism into Glasgow's Electroweak Theory, giving it its modern form. The Higgs mechanism is believed to give rise to the masses of all the elementary particles in the Standard Model. This includes the masses of the W and Z bosons, and the masses of the fermions, that is the quarks and leptons. After the neutral weak currents caused by Z boson exchange were discovered at CERN in 1973, the Electroweak theory became widely accepted and Glasgow, Salam, and Weinberg shared the 1979 Nobel Prize in Physics for discovering it. The W and Z bosons were discovered experimentally in 1981, and their masses were found to be as the Standard Model predicted. The theory of the strong interaction, to which many contributed, acquired its modern form around 1973–74, when experiments confirmed that the hadrons were composed of fractionally charged quarks. Overview: at present, matter and energy are best understood in terms of the kinematics and interactions of elementary particles. To date, physics has reduced the laws governing the behavior and interaction of all known forms of matter and energy to a small set of fundamental laws and theories. A major goal of physics is to find the common ground that would unite all of these theories into one integrated theory of everything, of which all the other known laws would be special cases, and from which the behavior of all matter and energy could be derived. Particle content: the Standard Model includes members of several classes of elementary particles, which in turn can be distinguished by other characteristics, such as color charge. Fermions: the Standard Model includes 12 elementary particles of spin 1/2 known as fermions. According to the spin statistics theorem, fermions respect the Pauli exclusion principle. Each fermion has a corresponding antiparticle. The fermions of the Standard Model are classified according to how they interact. There are 6 quarks, and 6 leptons. Pairs from each classification are grouped together to form a generation, with corresponding particles exhibiting similar physical behavior. The defining property of the quarks is that they carry color charge, and hence, interact via the strong interaction. A phenomenon called color confinement results in quarks being perpetually bound to one another, forming color-neutral composite particles containing either a quark and an antiquark or 3 quarks. The familiar proton and the neutron are the 2 baryons having the smallest mass. Quarks also carry electric charge and weak isospin. Hence they interact with other fermions both electromagnetically and via the weak interaction. The remaining 6 fermions do not carry color charge and are called leptons. The 3 neutrinos do not carry electric charge either, so their motion is directly influenced only by the weak nuclear force, which makes them notoriously difficult to detect. However, by virtue of carrying an electric charge, the electron, muon, and tau all interact electromagnetically. Each member of a generation has greater mass than the corresponding particles of lower generations. The first generation charged particles do not decay. Hence all ordinary matter is made of such particles. Specifically, all atoms consist of electrons orbiting atomic nuclei ultimately constituted of up and down quarks. Second and third generations charged particles, on the other hand, decay with very short half-lives, and are observed only in very high-energy environments. Neutrinos of all generations also do not decay, and pervade the universe, but rarely interact with baryonic matter. Gauge bosons. In the Standard Model, gauge bosons are defined as force carriers and mediate the strong, weak, and electromagnetic fundamental interactions. Interactions in physics are the ways that particles influence other particles. At a macroscopic level, electromagnetism allows particles to interact with one another via electric and magnetic fields, and gravitation allows particles with mass to attract one another in accordance with Einstein's theory of general relativity. The Standard Model explains such forces as resulting from matter particles exchanging other particles, known as force-mediating particles. When a force-mediating particle is exchanged, at a macroscopic level the effect is equivalent to a force influencing both of them, and the particle is therefore said to have mediated that force. The Feynman diagram calculations, which are a graphical representation of the perturbation theory approximation, invoke force-mediating particles, and when applied to analyze high-energy scattering experiments are in reasonable agreement with the data. However, perturbation theory fails in other situations. These include low-energy quantum chromodynamics, bound states, and solitons. The gauge bosons of the Standard Model all have spin. The value of the spin is 1, making them bosons. As a result, they do not follow the Pauli exclusion principle that constrains fermions, thus bosons do not have a theoretical limit on their spatial density. The different types of gauge bosons are described below. Photons mediate the electromagnetic force between electrically charged particles. The photon is massless and is well described by the theory of quantum electrodynamics. The W+, W, and Z gauge bosons mediate the weak interactions between particles of different flavors. They are massive, with the Z being more massive than the W plus or minus. The weak interactions involving the W plus or minus exclusively act on left-handed particles and right-handed antiparticles only. Furthermore, the W plus or minus carries an electric charge of +1 and a 1 and couples to the electromagnetic interaction. The electrically neutral Z boson interacts with both left-handed particles and antiparticles. These 3 gauge bosons along with the photons are grouped together, as collectively mediating the electroweak interaction. The 8 gluons mediate the strong interactions between color-charged particles. Gluons are massless. The eightfold multiplicity of gluons is labeled by a combination of color and anti-color charge. Because the gluons have an effective color charge, they can also interact among themselves. The gluons and their interactions are described by the theory of quantum chromodynamics. The interactions between all the particles described by the Standard Model are summarized by the diagrams on the right of this section. Higgs boson. The Higgs particle is a massive scalar elementary particle theorized by Robert Brout, Franz Section Engelert, Peter Higgs, Gerald Goralnik, Sia Hagen, and Tom Kibble in 1964 and is a key building block in the Standard Model. It has no intrinsic spin, and for that reason is classified as a boson. The Higgs boson plays a unique role in the Standard Model, by explaining why the other elementary particles, except the photon and gluon, are massive. In particular, the Higgs boson explains why the photon has no mass, while the W and Z bosons are very heavy. Elementary particle masses, and the differences between electromagnetism and the weak force, are critical to many aspects of the structure of microscopic matter. In electroweak theory, the Higgs boson generates the masses of the leptons and quarks. As the Higgs boson is massive, it must interact with itself. Because the Higgs boson is a very massive particle and also decays almost immediately when created, only a very high-energy particle accelerator can observe and record it. Experiments to confirm and determine the nature of the Higgs boson using the Large Hadron Collider at CERN began in early 2010, and were performed at Fermilab's Tivatron until its closure in late 2011. Mathematical consistency of the Standard Model requires that any mechanism capable of generating the masses of elementary particles become visible at energies above 1.4 TeV. Therefore, the LHC was built to answer the question of whether the Higgs boson actually exists. On July 4, 2012, the two main experiments at the LHC both reported independently that they found a new particle with a mass of about 125 GeV-C2, which is consistent with the Higgs boson. Although it has several properties similar to the predicted simplest Higgs, they acknowledged that further work would be needed to conclude that it is indeed the Higgs boson, and exactly which version of the Standard Model Higgs is best supported if confirmed. On March 14, 2013, the Higgs boson was tentatively confirmed to exist. Full particle count, counting particles by a rule that distinguishes between particles and their corresponding antiparticles, and among the many color states of quarks and gluons, gives a total of 61 elementary particles. Theoretical aspects. Construction of the Standard Model Lagrangian. Technically, quantum field theory provides the mathematical framework for the Standard Model, in which a Lagrangian controls the dynamics and kinematics of the theory. Each kind of particle is described in terms of a dynamical field that pervades space-time. The construction of the Standard Model proceeds following the modern method of constructing most field theories, by first postulating a set of symmetries of the system, and then by writing down the most general renormalizable Lagrangian from its particle content that observes these symmetries. The global Poincare copyright symmetry is postulated for all relativistic quantum field theories. It consists of the familiar translational symmetry, rotational symmetry and the inertial reference frame invariance central to the theory of special relativity. The local SU3, SU2, U1, gauge symmetry is an internal symmetry that essentially defines the Standard Model. Roughly, the three factors of the gauge symmetry give rise to the three fundamental interactions. The fields fall into different representations of the various symmetry groups of the Standard Model. Upon writing the most general Lagrangian, one finds that the dynamics depend on 19 parameters, whose numerical values are established by experiment. The parameters are summarized in the table above. Quantum Chromodynamic Sector. The quantum chromodynamic sector defines the interactions between quarks and gluons, with SU3 symmetry, generated by TAR. Since leptons do not interact with gluons, they are not affected by this sector. The Dirac-Lagrangian of the quarks coupled to the gluon field is given by is the SU3 gauge field containing the gluons, are the Dirac matrices, D and U are the Dirac spinors associated with up and down type quarks, and GS is the strong coupling constant. Electroweak sector. The electroweak sector is a Younger-Mills gauge theory with the simple symmetry group U1, SU2, L, where B1/4 is the U1 gauge field. YW is the weak hyperchagia the generator of the U1 group. Is the three-component SU2 gauge field. Are the Pauli matrices infinitesimal generators of the SU2 group. The subscript L indicates that they only act on left fermions. Ga squared and G are coupling constants. Higgs sector. In the Standard Model, the Higgs field is a complex spinor of the group SU2, L, where the indices plus and 0 indicate the electric charge of the components. The weak isospin of both components is 1. Before symmetry breaking, the Higgs Lagrangian is which can also be written as tests and predictions. The Standard Model predicted the existence of the W and Z bosons, Gluon, and the top and charm quarks before these particles were observed. Their predicted properties were experimentally confirmed with good precision. To give an idea of the success of the SM, the following table compares the measured masses of the W and Z bosons with the masses predicted by the SM. The SM also makes several predictions about the decay of Z bosons, which have been experimentally confirmed by the Large Electron-Positron Collider at CERN. In May 2012, Bar Collaboration reported that their recently analyzed data may suggest possible flaws in the Standard Model of particle physics. These data show that a particular type of particle decay called beta d star tau nu happens more often than the Standard Model says it should. In this type of decay, a particle called the B-bar meson decays into a d meson, an entire neutrino and a tau lepton. While the level of certainty of the excess is not enough to claim a break from the Standard Model, the results are a potential sign of something amiss and are likely to impact existing theories, including those attempting to deduce the properties of Higgs bosons. On December 13, 2012, physicists reported the constancy, over space and time, of a basic physical constant of nature that supports the Standard Model of physics. The scientists, studying methanol molecules in a distant galaxy, found the change in the proton-to-electron mass ratio I1/4 to be equal to 0.0 plus or minus 1.0 10^7 at redshift z equals 0.89, and consistent with a null result. Challenges. Self-consistency of the Standard Model has not been mathematically proven. While regularized versions useful for approximate computations exist, it is not known whether they converge in the limit that the regulator is removed. A key question related to the consistency is the Younger-Mills existence and mass gap problem. Experiments indicate that neutrinos have mass, which the classic Standard Model did not allow. To accommodate this finding, the classic Standard Model can be modified to include neutrino mass. If one insists on using only Standard Model particles, this can be achieved by adding a non-renormalizable interaction of leptons with the Higgs boson. On a fundamental level, such an interaction emerges in the seesaw mechanism where heavy right-handed neutrinos are added to the theory. This is natural in the left-right symmetric extension of the Standard Model and in certain ground unified theories. As long as new physics appears below or around 1014 a GeV, the neutrino masses can be of the right order of magnitude. Theoretical and experimental research has attempted to extend the Standard Model into a unified field theory or a theory of everything, a complete theory explaining all physical phenomena including constants. Inadequacies of the Standard Model that motivate such research include, it does not attempt to explain gravitation, although a theoretical particle known as a graviton would help explain it, and unlike for the strong and electroweak interactions of the Standard Model, there is no known way of describing general relativity, the canonical theory of gravitation, consistently in terms of quantum field theory. The reason for this is, among other things, that quantum field theories of gravity generally break down before reaching the Planck scale. As a consequence, we have no reliable theory for the very early universe. Some consider it to be ad hoc and inelegant, requiring 19 numerical constants whose values are unrelated and arbitrary. Although the Standard Model, as it now stands, can explain why the neutrinos have masses, the specifics of neutrino mass are still unclear. It is believed that explaining neutrino mass will require an additional 7 or 8 constants, which are also arbitrary parameters. The Higgs mechanism gives rise to the hierarchy problem if some new physics is present at high energy scales. In these cases, in order for the weak scale to be much smaller than the Planck scale, severe fine-tuning of the parameters is required. There are, however, other scenarios that include quantum gravity in which such fine-tuning can be avoided. It should be modified so as to be consistent with the emerging Standard Model of cosmology. In particular, the Standard Model cannot explain the observed amount of cold dark matter and gives contributions to dark energy which are many orders of magnitude too large. It is also difficult to accommodate the observed predominance of matter over antimatter. The isotropy and homogeneity of the visible universe over large distances seems to require a mechanism like cosmic inflation, which would also constitute an extension of the Standard Model. Currently, no proposed theory of everything has been widely accepted or verified. See also: fundamental interaction, quantum electrodynamics, strong interaction, color charge, quantum chromodynamics, quark model, weak interaction, electroweak theory, Fermi theory of beta decay, weak hypercharge, weak isospin. Gauge theory, non-technical introduction to gauge theory, generation, Higgs mechanism, Higgs boson, Higgsless model, J. C. Ward, J. J. Sakurai Prize for Theoretical Particle Physics, Lagrangian, Open Questions, BTeV experiment, CP violation, neutrino masses, quark matter, penguin diagram, quantum field theory, Standard Model, mathematical formulation of, physics beyond the Standard Model, on particle physics, notes and references. References. Further reading, Arawerta. The Theory of Almost Everything, The Standard Model, The Unsung Triumph of Modern Physics. Plumer, B. A. Schum. Deep Down Things, The Breathtaking Beauty of Particle Physics. Johns Hopkins University Press. ISBN A0-8018-7971-X. Introductory Textbooks, I. Aitchison, A. Hay. Gauge Theories in Particle Physics, A Practical Introduction. Institute of Physics. ISBN A978-0-585-44550-2. W. Greiner, B. Ma 1/4 Lair. Gauge Theory of Weak Interactions. Springer. ISBN A3-540-67672-4. G. D. Coughlin, J. Dodd, B. M. Griperos. The Ideas of Particle Physics, An Introduction for Scientists. Cambridge University Press. D. J. Griffiths. Introduction to Elementary Particles. John Wiley & Sons. ISBN A0-471-60386-4. G. L. Kane. Modern Elementary Particle Physics. Perseus Books. ISBN A0-201-11749-5. Advanced Textbooks, T. P. Cheng, L. F. Lee. Gauge Theory of Elementary Particle Physics. Oxford University Press. ISBN A0-19-851-961-3. Highlights the gauge theory aspects of the Standard Model. J. F. Donoghue, E. Golowich, B. A. Holstein. Dynamics of the Standard Model. Cambridge University Press. ISBN A978-0-521-47652-2. Highlights dynamical and phenomenological aspects of the Standard Model. Elo Rifat. Group Structure of Gauge Theories. Cambridge University Press. ISBN A0-521-34785-8. Nagashima Y. Elementary Particle Physics, Foundations of the Standard Model, Volume 2. 920 N Euro Th degree Thn Florin N. Schwartz, M.D. Quantum Field Theory in the Standard Model 952 pages, Launjacker P. The Standard Model and Beyond. 670 pages highlights group theoretical aspects of the Standard Model. Journal articles, E. S. Abers, B. W. Lee. Gauge Theories. Physics Reports 9, 1 Euro 141. Bibcode, 1973 PHR, 9, 1A doi, 10.1016/0370-1573, 73, 90027-6. M. Bork et al. The Electroweak fit of the Standard Model after the discovery of a new boson at the LHC. The European Physical Journal C72. A.R. Ziv, 1209.2716. Bibcode, 2012 EPJC. 72.2205b doi, 10.1140S10052-012-2205-9. Y Hayato al search for proton decay through PAI 1/2 K+ in a large water Shankov detector. Physical Review Letters 83, 1529. AR Ziv, HEPX/9904020. Bibcode, 1999 PHRVL 83.1529H doi, 10.1103/Phys Rev Let 83.1529A, SF Novas. Standard Model, An Introduction. AR Ziv, HEP-PH/00012830, HEP-PH. D.P. Roy. Basic Constituents of Matter and Their Interactions A Progress Report. AR Ziv, HEP-PH/9912523, HEP-PH. F. Wilcock. The Universe is a Strange Place. Nuclear Physics B, Proceedings Supplements 134, 3. AR Ziv, Astro PH/040137. Bibcode, 2004 New PHS 134, 3W doi, 10.1016/J Nickel-Physps. 2004.08.001 External links. The Standard Model explained in detail by CERN's John Ellis Omega Tau podcast. LHCC's Hint of Lightweight Higgs Boson New Scientist. Standard Model may be found in Complete, New Scientist. Observation of the top quark at Fermilab. The Standard Model Lagrangian. After electroweak symmetry breaking, with no explicit Higgs boson. Standard Model Lagrangian with explicit Higgs terms. PDF, PostScript, and LaTeX versions. The Particle Adventure. Web tutorial. Knobs, Matthew. Introduction to the Standard Model of Particle Physics on Kuro 5 Hin, Part 1, Part 2, Part 3A, Part 3B. The Standard Model. The Standard Model on the CERN website explains how the basic building blocks of matter interact, governed by four fundamental forces: